get started. Now that almost finishes chapter 4. Almost. We have one more little example here that I said we would go over for chapter 4, and that's where we're at right now. And it's going to be that operations management example that's up there. Here we go, chapter 4, last example, operations management. We'll start right here. This company, Chandler's company, markets various business and engineering products. Currently, they're preparing to introduce 2 new calculators. And these are going to be new products, one's for the business market, one's for the financial market. The engineering market called for, they're going to call it the technician. So when you see the technician calculator, that's the financial one. The other one they're calling, what do they call the other one? Can't see it. Each calculator has 3 components. There's the base, which can be used for either calculator, it's interchangeable. So however many bases we're making, we're the company who's going to put this order together. And we realize we can't make all these ourselves. And we're going to have to subcontract this. This is real life. Many manufacturing companies will get orders that are so big they realize we can't fit it into our schedule for whatever reason. They subcontract another manufacturing company that maybe they already have a relationship with, that they share the tooling, the die, or whatever's involved so they can make the exact same product with the same specs as if it's being made by your company. But they have to make money. So it costs you so much to make it, it costs them so much to make it. They have to make money, so it's going to cost you more for every one you have subcontracted out to the other company you have a relationship with. So you want to try to make as many as you can to keep your profit margin as high as possible. And you're cutting into the profit margin for all those that are made by this other company because you've already submitted your bid at one price. You can't all of a sudden say, oh, but these 50 over here, we had to get someone else to make, so we got to increase the price. No, that's it. The contract's done and over with. You can't go back to them and say that. You received a purchase order. That's like cash. That's their promise. They're going to pay you for what you put a bid on. And that bid was based on you making them all, and now you realize you can't make them all. That's where this is going. So, let's jump here. The financial calculator uses a base, a cartridge, and a top. It has its own top, has its own cartridge, but the base is the same for both these calculators. The technician calculator, same base, the cartridge, the top. If we can make these ourselves, as many as we can make, look at our cost. But if we have to subcontract this other company that we have a relationship with, you can see there's an increase on every item. Our cost, which eats into our profit, because we've already bid this at the price as if we were making all of it. So we want to keep this as low as possible. Do you think this is a maximization or minimization problem to solve? Minimization, keeping costs as low as possible, and what combination now of what we're going to make will allow us to keep that cost as low as possible, because then our profit margin will be as much as we possibly can get in this situation. What other restrictions we got here? How many do we have to make? Company is forecasting that they need 3,000 financial calculators, 2,000 technician calculators. However, there's capacity, manufacturing capacity is limited. The company has only 200 hours in regular manufacturing time, and then there's 50 hours of overtime available. That's it for us making our own. Whatever we can't fit into 200 hours, plus possibly 50 hours of overtime, which is going to cost us more money, so we got to try to figure out, is it better to use the overtime or subcontract those out also? And every one of the hours that we use overtime to make it ourselves is an extra $9. Right? Every hour overtime we use is an extra $9 added to our cost off the product. Here's how much time in minutes each part takes if we make it ourselves. So think about that. The time to make the items is in minutes, but the time that's available is in hours. That's the tricky part of this. It's not that tricky now that I kind of emphasized it, but you have to catch it. That's what you're heading towards. You're going to be getting more of these problems where it's talking about seconds and minutes, minutes and hours. And you got to make sure you have the same units of time on the left side and right side of a constraint. That's the big deal. So now that I told you that, if I were taking, first of all, I almost forgot, how many decisions do you see? Name one decision. You're the person in charge of this project. Your goal is to schedule to make as many as possible in order to keep your costs as low as possible. What's the decision you have to make? How many what? How many bases we're going to make? Yes. What else? There's one. What else?
How many financial cartridges?
How many financial cartridges we're going to make? How many technician cartridges we're going to make? How many financial tops we're going to make? How many financial or technician tops we're going to make? Is that 5? How many bases we're going to buy from our subcontractor? That's 6. How many financial cartridges we're going to buy from the subcontractor? 7. How many technician cartridges, how many financial tops, how many technician tops we're buying from the subcontractor? We have 10 variables, 10 decisions. Now, all of those 10 questions have to be answered to put together the production process. At the same time, we're telling the manufacturing to get going, they need to know exactly how many bases. They said, we want to start with bases. How many? We're waiting for the number. Let's go. Time is money. At the same time, the other company is going to be making theirs the same time we're making ours, so we can deliver the whole order in one shot. So they're waiting to hear how many bases they're supposed to make also. Those are the 10 decisions. We're going to BM, BP, FCM, FCP, TCM, and T. So B is going to be bases. M means we're making it ourselves. P is we're purchasing it from our subcontractor. Here's the cartridges we're making, financial cartridges we're purchasing. Technician cartridges we're making, technician cartridges we're purchasing, and so on and so on. There's our 10 variables. Now, let's go back to this. Let's write a constraint. One of the limitations were that we only have 200 hours available in manpower to make these, no matter what we're making. I got to represent the limit we have in 200 hours, less than equal, greater than equal. We're equal. 200 hours, less. That's all the time we have to make. You're the scheduling the manufacturing. Is this going to be less than equal, greater than equal, or equal? Less than equal. Less than equal. Now, if I write 200 here, then it's in hours. And I got to make all of these variables and how much time they're going to take up, then in hours. Instead, it'd be easier. I'm going to switch my 200 hours to minutes. What is that, 12,000 minutes? Is that right? 12,000 minutes. So now I can take all the variables that represent that's going to use up this time. Out of the 10 variables, only 5 of them are manufacturing time, so that's all that has to be on this side. All the purchasing variables are not part of this, because they're not going to go through the 200 hours that we have available. So I've got whatever the variable is for the base made. That would be B, is it M? BM times 1 is 1. I'm not going to put a 1 there. Plus 3 times whatever the financial M, is that FCM or FM? Nobody has the
FCM.
Thank you. Plus 2.5, whoops, where's my plus? 2.5 times the variable, this must be TCM. Plus 1 financial top, would that just be FTM by chance? Just FM? FTM? FTM, just 1, so I'm not putting a 1 there. And then 1.5 plus 1.5 T, what is that, TTM? TTM. There's the constraint that represents that 12,000 minutes, or really 200 hours. Here's what's tough, all right? We only have 50 hours of overtime. The variable we're using for overtime is this variable, this extra variable called OT. That makes it 11. Overtime has to be less than or equal to 50. Now, why doesn't that have to be in minutes? Why is that now? The left side is in hours. OT is going to be the amount of hours we use in overtime. So the right side can be in hours also, which is less than or equal to 50. The objective function, where's that? Right there. Every variable multiplied by its cost, or hang on a minute, our cost per unit. What are, go ahead. Like for example, BM are our bases that we make. So we're going to minimize what is that, 50 cents? 0.5 times BM plus 0.6 times, what's the one we're buying? Is that BP? BP. Everybody get this? Plus $3.75 times financial cartridge manufactured, plus $4 times financial cartridge purchase. And we got to have all of those on there, all 10 of those. I'm putting dot, dot, dot. Because here it is right here. All the prices times that, and then we get to the overtime one. $9, the story says, for every hour of overtime, it's going to cost us $9. So however many hours of overtime we schedule, it's going to cost us $9. So we have it in the objective function because that's what we're trying to minimize is our cost. We find out, hang on, where's that? We know that we need 3,000 financial calculators and 2,000 technician calculators. You add that up, that means we need 5,000 bases. So however many bases we're making, plus however many bases we're going to get from the subcontractor, has to equal 5,000. That's exactly how many we need. However many financial calculator cartridges we make and we buy have to be 3,000. Technician cartridges, however many we make, plus however many we buy, has to equal 2,000. And then, what do we have here? Top, the technician, financial top we make plus buy is 3,000, and the technician also 2,000. So here's what's going on. We need 2,000 technician calculators, 2,000 tops, 2,000 cartridges, and out of this 5,000 bases, 2,000 of them go with that calculator. We need 3,000 financial calculators, 3,000 top, 3,000 cartridges, and out of that 5,000, 3,000 of those bases are for the financial limit. So there's those limitations. There's the overtime limitation. Here is the one we did the look. Right? Is this right here? BM plus 3, plus 2.5, plus 1 of those, plus 1.5, less than equal 12,000. Put it all up there, just like each constraint. Here's where our optimal solution is going to arrive. Here's all our costs times each variable's optimal solution. Ready? Data. Solver is D18. You can't see the numbers. I want you to see the numbers. Hang on. There we go. Now, solver. D18 is where the optimal solution is being, or the objective function value. It's a minimization on all those costs. We want to make the optimal solution go from D14 right there all the way over to, is it N14? Yes. Here's our constraints. All of these equal or all together right there. D21 through 25, there's an equal sign. G21 through 25. And then these bottom two are less than equal, so E26 and 27, less than equal. G26, 27. Are you ready? It is posted. All of these are posted.
What's it called? Financial?
It's called operations management example. Because you're scheduling operations. You ready? My question for you is, how many bases are we going to make ourselves?
All of them.
That's correct. Everybody here? He said all of them. All 5,000 bases we're making ourselves. Obviously, the difference between our cost of making it and the cost of getting it from the subcontractor is wide enough that we'd be better off keeping our costs low by making those ourselves. Is there anything that we're not making at all and that we're going to buy them all from the subcontractor? Is there anything up there you see that we're not making at all? There it is. FTM, so that would be the financial top manufacturer. We're going to get all 3,000 of those, the financial calculator, from the subcontractor. We're also not making the technician top. We're getting all those from the subcontractor. How many hours of overtime are we using? 0. No overtime. $9 an hour in overtime was too much. And that we're better off. It would have stopped us from subcontracting everything we're purchasing, which are some of the financial cartridges and these two tops. It would have stopped that, but the $9 an hour was more than the additional amount we got to pay to have the subcontractor make it. There's our combination right there. How many constraints are binding? Uh-oh. There's 7 constraints. How many are binding? I hear 6. Who said it? No one wants to take credit? It's correct. 6. You see the answer? Lake, where's the answer for this?
It's right above 7.
Right here. Look at how many have the left side equaling the right side. It's right there. No slack or surplus on any of them that equal on the left and right. This is the non-binding constraint. Only one was non-binding out of 7 constraints. What's our total cost to make and buy and fulfill all 5,000 of these for the customer? What's our total cost for open? Because we bid it, they're paying us, I think it's $50,000, no, it's like $45,000. Let me write this down. They're going to pay us $45,000. My question is, are we making money on this or are we losing money? We're making money because what's our total cost? That's right, $24,443, is that what it says, and 30 cents? 43 and 30 cents. And that's the lowest we can get our total cost in this particular situation. There may be another combination. We could maybe make these instead of buying or something, some other combination that could possibly tie this, but why spend the time looking for it? There's no combination that will get us below this. This is the lowest you can get. Many of these have what are called alternative solutions, but there's no reason to go after an alternative solution unless you're in a special circumstance where you need to. Go with the recommendation you got there, because there's no alternative solution that will get you lower than this. There may be something to tie it, but nothing will get you lower. So you might as well go for it like this. So, that's the end of chapter 4. The goal is that you can read a story, you can write the objective function, you can identify the variable, you can write the constraint, unless there's overtime involved. I can't do it, you can. I don't expect you to. And then you got to be able to look at the Excel spreadsheet. You got to know what was entered here, what was entered there. If the solver's open, you got to know what was entered there. If I ask you to tell me what you would enter in a solver for the 3rd constraint, you got to know what the left side would be, what the symbol would be, what the right side would be, what it would look like. All right? And then you got to be able to answer questions. How many calculator times are we going to be making? How many financial cartridges are we going to be buying for the subcontractor? You've got to be able to read this output and answer those questions. We've taken everything from chapter 1 now, and we're all the way through. You've now learned pretty much everything stacked on top of everything. And now as we move past chapter 4, chapter 6 is like a career all on its own using this. Chapter 9 is a whole different career using this. Chapter, what's after 9? 12, 11, excuse me. 11, it's a different story. Some people find 11 is one of the hardest chapters of the semester, so be here for that lecture, please, because I simplified for you. Chapter 12, simulation, you're using some of the stuff. Chapter 15, forecasting. So at this point, every chapter after this are kind of they stand on their own, they represent a whole different way of using this kind of stuff. And now you're at the point where you have all the building blocks to be able to do linear programming. It's just a matter of how now to use it from this point on.
Yeah. Where's you said that?
Well, I made that up. I said, let's pretend that we bid this at $45,000, and we got a, what's it called? And we got
I see what you're saying.
something from them that says, we accepted your bid at $45,000, but our costs are higher than what we expected when we did the bid, because we have to subcontract so much of this out at an additional price. Luckily, the profit is still pretty darn good. It's worth it. Okay, chapter 6. You ready? Logistics. Tell me you've heard that before.
Yeah.
Good entry-level job when you're out of college if you like operations management, if you like supply chain management. If you're an SCM major, Logistics specialist is a great entry-level job to get your feet wet. Logistics, before even the word was invented, I was working at this manufacturing company in Ohio called Artesian Industries. And we made everything you can imagine in the bathroom. And we had a person doing logistics, but we never called her our logistics specialist because the word didn't exist yet. I'm going back to the 1980s. But really what she was doing is we were one of the few manufacturers that owned our own trucks. So we shipped our own goods because we made so many different items, we could fill a whole truck worth of stuff and ship it out. She would schedule which trucks are going in which direction and what the route is, and the trucks had to be loaded. Now I want to make sure you hear this. So that the very last drop-off is at the front of the truck. The very first drop-off is in the back. And so everything's planned out. As that truck goes to deliver, the person's taking it off the back is their order up to a point. The truck then goes to the next stop, their order's right there in the very back, and it goes on, and the last stop is the stuff that's all right in the front, everything's in order, so nothing gets screwed up. That's part of logistics, making sure everything's loaded, just whatever that route is that got scheduled. But the deal was, this is where we were losing money, is our trucks then had to come back. You try to get a circle where they're already on their way back, but it doesn't always work out that way. As a matter of fact, many times, a truck would be empty for almost 3/4 of the distance coming back. And this is where logistics, this is where she was like the diamond in the rough. Because she figured out, we had relationships with companies all over the United States. And we knew, we go to these trade shows, we have all these different hardware places and manufacturers of other things in bathrooms or the house. And so she would get a hold of these companies who needed to get things east. We were in Mansfield, Ohio. Who needed to bring things back to Ohio or Indiana on the way back from the west. And the truck would stop and pick up their stuff and bring it out. And that's where the trucks then paid for themselves. Is due to the fact that it was picking up stuff and we were making money on that coming back. And that's what logistics does. It allows the companies, especially that own their own trucks, to have other items to be able to ship back instead of an empty trailer coming back that you're paying for the whole way. And so a logistics specialist is on the phone all the time. Hey, do you have anything that needs to come back? We have a truck coming by on this day in the morning. You got anything that needs to come east? Or wherever you're located. So if you like this chapter, this is all about scheduling, shipping, and planning, this kind of stuff called logistics. This whole chapter is one job. I'm going to try to make it easy for you. So I posted this list of topics and I updated it this morning to add a little bit to it. So if you printed it before this morning, you want to reprint this or rekeep it. Network models. We're going to learn 5 of them. Transportation, transshipment, assignment, shortest route, max flow. We'll try to get through 3 of these today. We may not. We may only get through 2. We'll see how far we get. Here's my hint. This is what you won't find in the book. When you see these network models drawn out, there's these big circles called nodes. It's literally telling you how many constraints there are. Every node is a constraint. Right there. And these nodes have lines hooking them together. Hey, this shipment could go to this node, but it can't go to this one, so there's no line there. This company could ship to this one, or this one, but maybe not that one. Every time you see a line, it's called an arc, and it's a variable. So the arcs are variables. So when you look at a network drawing, and you're analyzing it, and the question says, how many constraints are there? Just count the nodes. How many variables are there? Count the arcs. That really simplifies this. So now, let's look at this. Again, how many constraints are there? How many? How many constraints? No, almost. How many big circles do you see? Circles, big circles. Big circles. Oh yes, 7. Yeah. I always saw 3, right? 3 on the left. 6. 7. 7 constraints. How many variables do you see? Now, give me a chance to add them. Okay, how many? How many variables are there? 12. 12 arcs. Get it?
No.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the arcs, right there. If you have another arc right here, going from here to here, that's another variable. Here, we're going to agree to do the variables like this. If on the left are called our supply, where things are coming from, on the right is where they need to go to, shipping or mailing, however. That's where it needs to go to. This is how many items we have available where it's coming from each location. This is how many items we need to get to each of these locations. Right? So that's our supply and demand. Jump in.
So will it always look like that? Like
No, they don't always look like that. Matter of fact, sometimes they look like this. Hang on. Ah.
Oh.
How many constraints are there? Hang on, I gotta look. I heard it. 8. 8 nodes. You see them? There's 8 constraints. So when you're going to be asked to be writing some constraints, using some variables. Okay, how many variables are in this problem? Let me look for. 12. I say 12 also. 12. 2, 4. Here's another 4 makes 8. Another 4 makes 12, right? Those are arcs. You see how it goes from one spot, has an arrow where it's going to? That arrow's telling you that's an arc. Now be careful. Wednesday, we have some that have an arrow in each end, meaning it can go either direction. And that's 2 variables.
But the black lines are not variables.
What? These are just pointing out things.
Just pointing out.
Just pointing out things. All right? You get it? All right. Let's go back here. Is that where we're at right here? Okay, ready? You told me there's, 4, 8, 12 variables there. Look at how we numbered the nodes. We started with 1 and went down to how many nodes we had? 1, 2, 3. And you can number the right-hand nodes anything you want. You could have went 4, 5, 6, 7, or 1, 2, 3, 4. Whatever numbers you use on your nodes are representing how you distinguish the name of the variable. You ready? Every arc is a variable. If this arc at the top, we need to name it. It's going from node 1, going to node 1. That's x11. That arc's variable name is x11. Now that you see it, what is this variable right here, right there? What is that one? X what? 3, 4. You've got it. Got you. This is almost too easy, right?
Does that tell you to reference them in the question?
How you're going to reference them, because you're going to write an objective function and you're going to write constraints. There's going to be a story, and that story is going to lead you to maybe drawing this, or you might be given this. Then once this is drawn, you use this to write your objective function constraints. Your objective function is either max or min. Every variable, which you told me there's 12, in the objective function, I want to make sure everybody hears me like, okay, ready? In the objective function is the only time you're using these numbers on the arcs. Those numbers represent, in most cases, the cost to ship that, or the amount of miles. Usually you're wanting to minimize something. This could be amount of time, this could be the cost, this could be the amount of miles. It's almost always minimized in most cases. I'm not going to try to trick you. In most cases, this is always minimized. And it's the only time you use those numbers is in the objective function. So I'm just going to start the objective function so you can see what the process is. I'm going to start at the very top, coming out of Cleveland, going to every one of our demands. So I've got min, and then I've got exactly 3x11 plus 2x12 plus 7x13 plus, is everybody getting this? Should I keep going? Okay, keep going. I heard some. There we go. I forgot what's after 7 here. Is that 5 or 6? Is that 6?
Looks like 6, man.
6x14 plus, I'm going down to the next one, 7x21 plus 5x22, dot, dot, dot. I think you get it now.
Somebody got it.
What? That's all right. This one, 4 times x34, 5 times x34, every variable is in the objective function with that number, which probably represents cost or something. Now, I did things backwards. We jumped to the end. And in fact, I want to stay at the end. Before we go to the story, I want you to see one more thing. You ready? Let's write a constraint. You told me there's 7 constraints because there's 7 nodes. Here's my hint on writing a constraint. You look at the node you're writing the constraint for, and if there's every arc that touches it is the variable that's on the left-hand side of the constraint. Let me repeat that. Look at a node you're going to write a constraint for. Count how many arcs touch that node, either coming out of it or going into it, one or the other. I'm going to randomly pick this one. How many variables would be on the left-hand side if I were writing this constraint right now? How many? 3. There's 3 arcs touching it. All right? So any one of these right now, you can tell me how many variables should be on the left. Right here, how many variables should be on the left side of this constraint? 4 variables. I'm going to write one. You ready? Here's the trick on transportation. Supply nodes are always less than equal. Let me repeat that. On a transportation, which is what we're talking about, a supply node constraint is always less than equal whatever it can be supplied. If I talk about that first constraint right there, Cleveland, I know the right side is less than equal to 5,000. So, let's do that one right up here. I'm doing Cleveland, the first node, top left, less than equal to, what did I say, 5,000? You told me how many variables are on the left side. How many variables are on the left side of this constraint? 4. Now, you write these variables, just follow the arcs, but do not include the costs that are on the arcs. Those costs are only in the objective function. So on the left side, I'm going to have x11 plus x12 plus x13 plus x14 less than equal 5,000. Everybody see it? Follow the arcs. It's going from node 1 to 1, 1 to 2, 1 to 3, 1 to 4. Now, demand nodes. Either they're like distribution centers or they're customers. This is the big part, if it is customers. In a transportation model, the demand is always an equal constraint, not less than equal, not greater than equal, equal. We want to provide the customer, or whoever this is on the right, distribution center, with exactly what they ordered. I want to write Chicago. We're going to write the node for Chicago, or the constraint for node Chicago. What's the right-hand side? Less than equal, greater than equal? Equal. That was a trick question. 4,000, right? Is that the demand for Chicago? The left-hand side has how many variables? How many arcs? Because all the demand nodes are always equal. All the supplies always less than equal. So the right-hand nodes, the demand, are equal constraints. The left-hand side supply, less than equal. Equal 4,000. We're doing Chicago right now. I see 3 arcs touching it. It looks like it's x12 plus x22 plus x32. Those are the 3 arcs touching it. Just follow the lines. 1, 2, 2, 2, 3, 2, equal 4,000. At this point in time, you can write any constraint for any node up there. Agree? I can point at any one of them, and everybody here should be able to tell me what the constraint is. You just follow the arcs. You know if it's less than equal. If I say the left one, you know it's equal if I say the right one. Okay? And you all know how to write the objective function. It's every arc with its cost, or whatever the number represents. So we'd have 12 variables. That's all there is to this.
Are you going to hit us with 12
Here.
variables to write out?
Oh, yeah, look at this one. How many is this one? This one only has 12 also, doesn't it?
Right.
Okay, hang on. Look at this one. Hang on. How many? Oh, not that one. Come on. How many does this have? Only 9. No, don't get me wrong. There's a lot of them with more than 12. Just not on this PowerPoint. Okay, here we go. Here's the story now. transportation problem, blah, blah, blah. You read that at home before you got here. I know you did, because you had your homework in early. Go ahead.
On the right hand side, you're straight, shouldn't second number change? Because now you have node 1, node 2, node 3, right?
Look, hang on. I was looking at Chicago. Is that what you're talking about right here?
Yeah, but shouldn't it be the second number should change instead of the first one?
No. All of these are coming into 2. See the arrows coming in? The numbers of the arcs are always where it's coming from 2. So this arc right here touching this, coming from there, x, 1, 2. Coming from 1, going to 2. This arc, x, 2, 2. Coming from 2, going to 2. This arc coming from 3, going to 2. So x, 1, 2, 2, 2, 3, 2. On the constraints for demand, and this is a quick way how I used to grade it, the second number should always be the same. On the arcs for supply, the first number should always be the same. 1, 1, 1, 1. Where it's going 2, 2, 2, 2. That's kind of a good way to check yourself, is have that little rule down. If it's a supply constraint, the first number of the variable is always the same. 1, 1, 1, 2, 1, 3, 1, 4, 1, 1, 1. And if it's a demand, the second number is the same.
So could you have more than one line going from one of the nodes on the left to one of the nodes on the right? And if so, how would you?
No, you wouldn't have 2 lines going here to here. You'd only have 1 line. You're saying like 2 trucks, maybe?
Yeah, maybe.
So how about like 2
arrow.
different truck routes?
Give me an example.
Like, there's more than one way to get from Flint to Grand Lake, so there would
Okay.
be 2 different routes.
What you're saying is, this one could go here, but then go there, right?
No, like, you could.
Because that is possible. You'll find, you're coming up to something that will have arcs in here.
If it doesn't exist, that's fine.
It doesn't exist. Do you mean like going from here to here, then here?
No, I mean.
You can't have 2 arrows going to the exact same spot from the same spot, if that's what you're saying. I don't know.
So what I'm saying is there's more than one way to get from one place to another place.
Right, and this isn't exact, this doesn't represent the one way of getting there. It represents whichever way we would go from there to there, whichever way we take.
But there's more than one way you could go, is what I'm saying.
I see what you're saying. I don't know how much it would change this, though, having 2 alternatives. Like, if this represents, let's say this is $4,000 for the whole truckload or something, even if this goes slightly different route, it's still getting from York to St. Louis, and it's still going to cost us $4,000, whichever route it takes. But where we're heading, which is what I thought he was asking, is this truck could go to Lexington, then go to St. Louis, and you'll see a new arc here, and look at the direction it goes. And so in that case, when you got that, you cannot have the same number on the left as you do the right. Let me show you. We're heading to transshipment, which looks like this. Notice we don't have any other node listed with the number 1. We don't have any other node listed with the number 2. You have to use a different number for every node in this case. Let me give you an example. Let's say we went 1, 2, 1, 2, 1, 2, 3, 4. And I said to you, X11, that could be X11 here, or it could be X11 here. You don't know which one it is. That's why you can't use the same numbers when you have multiple nodes like this, in different, that you go in different orders. So we have to use a different number. When we get to, I don't know how far we're going to take this, but if we get to a point to where I add a node, let's say here, going from 3 to 4, I can't have X34 and an X34. So I have to renumber these 4, 5, 6, 7, so that we don't have any possibility of a 3, 4, I'm sorry, 3, 4, and then a 3, 4 again. You just can't tell the difference, and the computer won't be able to tell the difference either. All right, you ready? Now we're going to attach the story to what we just did.
We're going to start at the beginning now.
We're going to start at the beginning now. Let's consider this transportation problem faced by Foster Generators. The problem involves transportation of their products from the 3 plants that they're making these at to the 4 distribution centers they have in other parts of the country. They operate plants in Cleveland, Bedford, and York. Here's how much generators they could make. 5,000 at this one, 6 at that one, 2,500. Now, they have the capacity to make that many, but they don't have to make that many. If the demand is less than 13,500, that's why you're using less than equal. because they don't have to make that many, that just happens to be their capacity. I want to give you a heads up. If the capacity is less than the demand, I'm not going to put this on a quiz, but in real life, you have to form a dummy plant. And it has to have additional capacity to meet that demand. Then when you run this, whatever's coming from this dummy supply means they're on back order. And so we got to let those customers know, you know, we have, let's see, you know, we have 1,000 of your order coming, but the other 500 is on back order because we had more demand than we had in capacity to supply. I'm not going to put one that you have to add a dummy node to on the test. I just want to let you know they do exist, and it's fairly common. So, here's the three places that we have generators coming from. Here's the capacity. We would write 3 nodes on the left, we would put each of the capacities, you could throw the names in, and then number them, 1, 2, 3. Now, the story says, here's where we need to ship to. Go ahead, Jason, you might ask something?
No, I just realized why that there's the same numbers on each side. It took me a second. I was like, why is the same? Why is there 1, 2, 3, 1, 2, 3, and then now I get.
You don't have to have the same numbers. It's just how it's usually done. Here's where we got to get stuff to. These 4 distribution centers: Boston, Chicago, St. Louis, Lexington. And here's what they're asking for. What? They want this many. It says capacity, but that's how much they are demanding. Here's our demand for each of those. It just so happens demand equals supply, but in most cases that's not true. For this one, it happens to equal. We don't need to put a dummy node or anything, and we know all of it's going to be used. And if we happen to have put equal signs here by accident, we'll still get the right answer because what capacity we can supply happens to equal demand. But don't get fooled and put equal signs on these because in most cases these are not equal and not all of them are going to be made. We don't need all the supply in most cases. And then you draw the network. Here's the story. Here's our capacity coming from, here we can go to, and here is our cost. You'll see another little chart will say, going from Cleveland to Boston, $3 per unit being shipped. Going from Cleveland to Chicago, $2. There'll be another grid. You draw your network. You're going to draw the circles on the left for supply, the ones on the right. The other grid, maybe, that shows the cost. You're going to put arcs and put the numbers on top. Go ahead.
Are we doing really any math at this point to get to this picture? Or
No
we're
math yet.
We're reading it and just.
You're reading it, and you're writing your objective functioning constraints. You drew your network, and now you go, okay. Our objective functions is putting each node's arcs. Here's every arc. Put it all together. All 12 arcs with their cost. This is where that cost goes in the objective function. So the rest of the variable just says dot, dot, dot.
So you're going to take that in the quiz, right? Dot, dot, dot.
No, I'm not. 1, 1, 1, 2, 1, 3, 1, 4. 2, 1, 2, 2, 2, 3, 2, 4. 3, 1, 3, 2, 3, 3, 3, 4. 4, 1, 4, 2, 4, 3, 4, 4. 12 arcs, 12 variables in that objective function. The only place you put those cost numbers. Now, every place we're supplying, there's 3 supply nodes. Less than equal, less than equal, less than equal, the amount of their capacities. On the left, every arc that's touching that node, that variable's on the left, without the cost. This is the #1 mistake I see. No matter how much I'm emphasizing this right now, someone's going to put whatever that cost is for X11, what is it? They're going to put a 3. They're going to say 3X11, 4X12, whatever the numbers are. The costs are only in the objective function. These constraints only have the variables without the associated costs. Here is our demand constraints. There were 4 nodes on the right with demand. Here are how many? There are 3 arcs touching each one of those nodes, representing 3 variables. And they're all equal because we're meeting demand. That's our #1 priority, is to try to meet every order. Now we plug it in. Hang on, I made this. Where is it here? This is transportation. Here it is. I did this one a little differently, Just so you can see another way of doing it, I did the other two though back to the original way, but this is like, here is the grid of the cost. If we ship from Cleveland to Boston, it's $3 for every unit. From Cleveland to Chicago, $2. You just enter these numbers in. Cleveland could provide 5,000, Bedford could provide 6,000, York could provide 2,500, Boston has a demand for 6,000, Chicago, St. Louis, Lexington. Those numbers are just entered. There's no equation at the top, just the data. Here's your equation. I did it two different ways for you, because this may be the first time you're seeing, someone just mentioned this in my office today, I don't remember who it was. You're seeing some product. Some product. Here's an example of some product being used. Here's the old-fashioned way. Let's go here for a minute. X9, where is our, every one of these numbers? 3 E9 times the optimal solution for Cleveland, Boston. E, you see the numbers, and E24. Then it's, what is that? F9, F24. And then you got G9, G24, H9. Here, all these zeros are where your optimal solution is going to appear. Right? And this objective function, if you want a shortcut, you could do is what's called a, click at it, sum product. This is a shortcut to do that long thing where every one of those boxes are times this box. Sum product, parentheses. The left-hand corner, E9, all the way to the bottom right-hand corner, H11, comma. The left-hand top corner here, E24, all the way to the bottom right corner here, York, Lexington, which is H26. There's your objective function. I can put it both ways so you can see whichever way you want to do it. All of these are just zeros, but here we go. Right here, this is adding the total amount that would be shipped to Boston no matter where it's coming from. Right here is the total amount that would be shipped to Chicago no matter where it's coming from. Right here, you can tell everything shipped to St. Louis, everything shipped to Lexington. Here, everything added together being shipped out of Cleveland no matter where it's going. And there's only 5,000 available in Cleveland. Go down one. Everything being shipped from Bedford, no matter where it's going, and there's only 6,000 that can be shipped. See where this is going? Now there's a little part you can't see here. The sum of everything being shipped to Boston, it's got to equal 6,000. Boston ordered 6,000 of these. Chicago, 4,000. So, now look at this. This solver. This is different than you've seen before as far as how this is. Hey. Oh. You ready? The objective function, either one of these two squares, is set up for E19 right there. The optimal solution is going to be from E24 all the way to H26, E24 to H26. Your constraints. Every one of these are a constraint equal to that. So you have E27 equals E29. Then you have F27 equals F29, G27, G29, and H. These are constraints. I24 less than equal to, what is that, K24. So I24, K24, I25 to K25, I26 to K26. Less than equal. And that's it. You change it to simplex. My question for you is, how many is Cleveland going to be shipping? Hey, come on. How many is Cleveland shipping to St. Louis? How many of these generators get shipped from Cleveland to St. Louis? 0. What about going from Bedford to Chicago? 2,500. What is the lowest we can get this cost of shipping down to with all the different routes we're going to have to take to ship all these generators? 13,000, I can't remember what it adds up to here. 11, 12, 13,500 generators being shipped. What's our total cost? $39,500 to get all of these shipped out from our 3 locations to our other locations. How many is being shipped out of Bedford altogether? 6,000. Look at Bedford. 2,500 going here, 2,000 here, 1,500 here, 6,000, 6,000. Here's the left side, here's the right side. Do you see any slack? What I mean is where the amount being shipped is different than the amount available to be shipped, or the amount arriving is different than the amount that should arrive at that location. You see any slack? Zero. Slack doesn't exist. Because we had exactly 13,500 to ship and exactly